Welcome to AS Online. I am here to discuss about SSC JE revision session, especially from the material science. Myself, Madhushekar, faculty at AS Online. So, SSC JE, for this SSC JE exam, if we talk about material science, most of the questions from the material science are theoretical. 99.99% the questions are theoretical, and these questions are very simple. For this SSC JE exam, especially from this material science, for this SSC JE exam, they will ask you questions 5 to 8 questions they will ask you. Remember, 5 to 8 questions they will ask you. 5 to 8 questions they will ask you, and we will see from which topics these type of questions they will ask you. Now, if we talk about this syllabus for SSC JE, okay, the most important topic is material properties and testing. Most important topic this is. From this topic, they will ask you questions related to different mechanical properties of materials, like simple, what is ductility, what is malleability, what is proof stress, what is yielding point, otherwise how will you find the Young's modulus, what is true stress, what is true strain. This type of basic questions they will ask you from the material properties and testing. See, out of all these topics, the material properties and testing has more weightage. Okay, material properties and testing has more weightage. From this, good number of questions they are asking for your exam. And the second most important topic is iron cementite phase diagram, otherwise iron carbon phase diagram. Iron cementite or iron carbon equilibrium phase diagram. So from this phase diagram, they are asking good number of questions. Okay, na? They are asking good number of questions. Not only for this exam, any competitive exam you take, from the iron cementite phase diagram, they are asking very good number of questions. Maybe 2 questions, sometimes 3 questions. Even including gate also, they are asking questions from the iron cementite phase diagram. So for your exam also, definitely they will ask you some 2 questions minimum from this iron cementite phase diagram. And after that, they will ask you questions. They may not ask you manufacturing of iron, like what is blast furnace, all these things, but they will ask you questions related to steels, like types of steels, like low carbon steel, medium carbon steel, high carbon steel, what are the percentage of carbon in all these types of steels, what is an alloy steel. Okay, within the alloy steel, they will ask you questions like questions from stainless steel, questions from basic questions, okay, questions from stainless steel and high speed steel, questions from high speed steel, and also what type of alloying elements we are adding, what type of alloying elements we are adding to improve the mechanical properties of steel. This type of questions also they are asking for your exam. And next important topic is heat treatment of steel. So from the heat treatment of steel also, they are asking good number of questions. Heat treatment of steel, from that they are also asking good number of questions. And sometimes ferrous alloys means they are nothing but steels and cast irons. Remember, ferrous alloys are nothing but steels, different types of steels, and also cast irons, different types of cast irons. Sometimes they will ask you different types of cast irons. And from non-ferrous alloys, especially from non-ferrous alloys like aluminum alloys, copper alloys, okay na? Aluminum alloys, copper alloys, you should go through that. Okay, nickel alloys also, you should go through these type of alloys. They will ask you theoretical type questions. And sometimes questions they will ask you from non-metallic materials. Non-metallic materials like you take polymers, they'll ask you questions from the polymers. They'll ask you questions from the polymers. Sometimes they'll ask you questions from the ceramics. Sometimes they'll ask you questions from the ceramics, but rarely they'll ask questions from the composite. Right? And also, sometimes they will ask you questions from the crystal structures. Crystal structures like simple cubic structure, body-centered cubic structure, face-centered cubic structure. From these also they will ask you questions. So remember, once again I'll recall everything, on what topics you should focus. Remember, 5 types of crystal structures are there. Simple cubic, body-centered cubic, face-centered cubic, diamond cubic structure, hexagonal closed pack structure. From these 5 types of structures, there is a chance to ask one question. Next, from the mechanical properties, they will ask you definitions of different mechanical properties. So you should cover all the mechanical properties of materials, at least the basic definitions. Next is, from the iron cementite phase diagram, some 2 questions they will ask you. So you should focus the theoretical concept of this iron cementite phase diagram. Okay, theoretical concept of the iron cementite phase diagram. Next, they'll ask you some questions from the heat treatment of steel, and they'll ask questions from the non-ferrous alloys like aluminum alloys like that, and also from the polymers they will ask you questions. Right? We will see some of those questions here I am going to discuss, okay, so that by seeing these questions, by solving these questions, you will get a confidence. You'll get a confidence that like I can easily crack the SSC JE exam. Like that confidence you'll get by seeing these questions, because they are very, very easy questions. They'll ask questions from the material science that they are very, very simple questions. Right, we will see those questions. First, I'll discuss about from the material properties and testing. Now, what type of questions they'll ask, like basic questions. Now, see here, the property of a material by virtue of which a body returns to its original shape after removal of the load. Very simple, by removing load, if a material reaches to its original state, that we call it as elasticity. In case if a material will not regain back, that we call it as plasticity. Very simple question. Now, the property of a material which enables it to resist fracture due to high impact loads. Okay? High impact loads or sudden loads, it will resist the fracture, that we call it as a toughness. Toughness is the ability of material that will resist impact loads. Basic definition. Now see here, resilience of a material is important when it is subjected to. Resilience is nothing but it is the ability of material that can resist or that can absorb the energy within the elastic limit. So within the elastic limits, the best example you take springs. Spring is the best application for the resilience. Out of these options, if you see, it's not like fatigue, it's not like thermal stresses, it's like you can go with a shocking load, okay, resilience of material we can use, right? Now, in a tensile test on a mild steel specimen, the breaking stress as compared to ultimate tensile stress. See, if I consider the stress strain curve, let us consider the stress strain curve. The stress strain curve is like this. So this is the ultimate point, and this is the fracture point. So fracture point stress is less than the ultimate point. So B is the correct answer for this question. Okay, fracture point is less than the ultimate point, so that's why B is the correct answer for this question. Now, the material which exhibit the same elastic properties in all directions, we call it as isotropic material. Remember, this is a material, if the material properties are same, in all the directions, that we call it as isotropic material. C is the correct answer. Now, the property of a material which allows it to be drawn into a smaller cross-section area. So, by applying tensile test to the material, the cross-section area will decrease and the length will increase. That we call it as ductility of the material. Ductility of the material is nothing but ability of material that can be drawn into voids. So, sudden reduction in cross-section area is going to change. Now, to which of the following is the proof stress? Remember, the proof stress is related to yielding point. Suppose, let us consider the stress strain curve. Listen, this is a stress strain curve. Now, I want to find the yield point for this stress strain curve. Okay, so if I want to find the yield point for this stress strain curve, I am considering 0.02. Remember, 0.02% of offset strain I am considering. I am drawing the linear parallel line to the stress strain curve. So, there is an intersection point to the stress strain curve. This intersection point represents the yield strength of material, that we call it as a proof stress. So, the proof stress is related with the yielding point. The proof stress is related with the yielding point. So, C is the correct answer for this question. Right. Now, which of the curve is best suited for linear elastic hardening and plastic material? Linear elastic hardening. Remember, linear elastic hardening. Remember, this is a linear elastic and hardening process. So, see, this is the correct answer for this question. Okay, elastic and linear hardening process. So, C is the answer for this question. Now, mathematically, strain is defined as deformation per unit length. It's very simple question. Deformation per unit length is nothing but change in length by original length is nothing but a strain. Very simple question. Now, see here, the property of a material to break suddenly with a little or no deformation. If a material will break suddenly by applying load without any deformation, that we call it as a brittleness. It's a very, very simple question. Now, an alloy of nickel and iron that is easily magnetized and demagnetized can also be used in electrical equipments. So, remember, an alloy of iron and nickel is we call it as firm alloy. Iron and nickel alloy, we call it as firm alloy. This is a firm alloy. B is the correct answer for this question. Now, dash technique uses wear particle analysis using lubricating oil. Remember, lubricating oil. By using lubricating oil, we are analyzing the wear particle which is released from the machine. That we call it as a ferrography method. D, ferrography method we are using. Ferrography method we are using to analyze the wear particles in the lubricating oil. Now, what is ductility in steel? Remember, the ductility of material is measured in two ways. One is percentage decrease in length and percentage increase in length and percentage decrease in cross-sectional area. So, ratio of change in length to the original length, that is correct. Okay, ratio of change in length to the original strength, that is correct. Amount of strain a material can withstand before fracture, this is also correct. But here they are not asking the measurement of ductility, they are asking ductility of steel. Ductility of steel is nothing but amount of strain a material can withstand before fracture. So, D is the correct option for this question. Right. Dash is the ability of steel to resist stresses that are reversal in nature. We can say reversible stresses, completely reversible stresses are dynamic loads that is related to the fatigue strength. That is related to the fatigue strength, because reversible stresses are nothing but cyclic loads or dynamic loads. So, dynamic loads are measured with the help of failure of the dynamic loads, we call it as a fatigue. Resistance of fatigue loads, we call it as a fatigue strength. So these are the questions related to material properties and testing. So good number of questions they asked from the material properties and testing. Now next I am going to discuss some of the questions related to the crystal structure. Now the atomic packing factor is higher. The atomic packing factor is higher in which of the following cubic lattice system? Remember, for a simple cubic system 0.52, for a body-centered cubic system 0.68, for a face-centered cubic system 0.74, okay, 0.74, and a diamond cubic system 0.34. So now see here, okay, FCC is the correct answer for this question. Highest packing fraction is present in FCC structure. Simple question. Essential gradient of any hardened steel. Essential gradient of any hardened steel is hardened steel has a martensite. So martensite is present in the hardened steel, right? Steel containing perlite and ferrite. Remember, steel containing perlite. Remember, steel containing perlite and ferrite. Remember, it is like a soft and a tough material. We can say perlite and ferrite containing materials are soft materials because ferrite is a ductile material. Within the perlite also ferrite is present. So we can say a soft material and it has good ductility also we can say. Steel with the carbon below 0.8% of carbon. Below 0.8% of carbon steels, they are hypoeutectoid steels. Above 0.8% of carbon, they are hypereutectoid steel. Above 0.8% of carbon steels, we call it as hypereutectoid steel. Now, dash structure is obtained by us-tempering process in the heat treatment. Remember, us-tempering process. Remember, us-tempering process is nothing but, okay, two interrupted cooling mediums we are using. First is rapid cooling, second is, remember, first is a rapid cooling, second is isothermal cooling. Now, if I consider this is a TTT diagram, okay, now remember, us-tempering process means rapid cooling, isothermal cooling. So here I will get bainite material I will get. This bainite material has a good toughness, good ductility, okay, good strength. So answer for this question is bainite. B is the correct answer for this question, right? Now dash structure has maximum hardness. As you are familiar, if we cool the material with a fast cooling rate, then the hardness of the material will increase, strength and hardness of material will increase. So out of these, trusite is a high temperature tempering process, perlite is like normalizing or annealing, martensite is hardening, sorbite is a high temperature tempering process, right? So martensite has a high hardness. Hardness of martensite is very, very high. It is produced by hardening process, after heating the material, by quenching in water, we will get martensite. So C is the correct answer for this question. Now, dash structure can be studied with the naked eyes. Remember, very simple question, basic question. Macro structure you can study with the naked eyes, but even microstructure also not visible for us. Suppose if this is an iron rod, I can't see the microstructure without naked eyes. Only by using a microscope I can see that. So macro structure you can understand with our naked eyes. So D is the correct answer for this question. Now, austenite is a solid solution of carbon in iron, in dash iron. See, austenite is nothing but a gamma iron. Remember, austenite is nothing but a gamma iron. Listen carefully. This is austenite. Okay, this is a gamma iron. This gamma iron we call it as austenite. This gamma iron is also known as austenite. This austenite has a percentage of carbon up to 2.1% of carbon it has. So it is a gamma iron. C is the correct answer. Okay. It is a gamma iron. Okay, gamma iron. Simple question. Next. A compound of iron and carbon called iron carbide is known as, it's a very simple question, iron carbide. Remember, in an iron carbon alloy, okay, in an iron carbon alloy, every carbon atom is covalently bonded with 3 iron atoms. This is one, and this is one. The carbon atom is covalently bonded with 3 iron atoms. Now this we call it as 3 iron atoms, 1 carbon atom. This is iron carbide. This is iron carbide. It is also known as cementite. This is also known as iron carbide. This is also known as cementite. Its crystal structure is orthorhombic structure. Orthorhombic. Its crystal structure is orthorhombic structure. So that A is the correct answer for this question. A compound of iron and carbon called iron carbide is also known as iron carbide. It is also known as martensite. A is the correct answer for this question. Next, gamma iron has structure. See, remember, in an iron carbon alloy, remember, delta iron or delta ferrite crystal structure is BCC. And gamma iron, or it is also known as austenite, its structure is FCC. And alpha iron, it is known as a ferrite, again its structure is BCC. So this is allotropy of iron. This we call it as allotropy of iron. So this allotropy of iron, remember, delta iron BCC, gamma iron FCC, and alpha iron is BCC. So gamma iron has what type of structure? BCC structure. Gamma iron has what type of structure? BCC structure. Gamma iron has BCC structure. Next, carbon percentage present in iron more than 4.3 is known as what? Listen, 2-3 times they ask this question, so I'll give you clarity. Listen carefully. This model question they asked 2-3 times now. Now see here. Suppose this is a partially drawn iron cementite phase diagram. Remember, up to 0.8% of carbon, remember, this is 0.8% of carbon. This is known as hypoeutectoid steel. Hypoeutectoid steel. From 0.8 to 2.1. From 0.8 to 2.1% of carbon, it is hypereutectoid steel. 0.8 to 2.1, it is known as hypereutectoid steel. From 2.1 to 4.3 or 4.2% of carbon, hypoeutectic cast iron. Hypoeutectic cast iron. 4.3 to 6.67. 4.3 to 6.67, it is hypereutectic cast iron. 4.3 to 6.67, it is known as hypereutectic cast iron. So carbon percentage more than 4.3. More than 4.3 is hypereutectic cast iron. Hypereutectic cast iron. D is the correct answer for this question. D is the correct answer for this question. It's a very simple basic question. Now, when solidification starts, iron will appear in the dash form. See, so many questions from the iron cementite phase diagram I am saying now. See, solidification starts. Listen carefully. Listen carefully. This is the diagram, partially drawn diagram. Okay. Listen. So here listen carefully, this is the liquid, okay. By cooling the liquid material, initially delta iron is formed, delta plus liquid, delta plus gamma, this is gamma iron at room temperature alpha. So solidification starts from delta iron. Remember, this is a liquid. So solidification starts from delta iron. So C is the correct answer for this question. C is the correct answer for this question. It's a very simple question. Now, cementite has a chemical formula I also discussed. Cementite, I said 3 iron atoms, 1 carbon atom. Cementite is what? 3 iron atoms, 1 carbon atom. This is known as a cementite and its structure is orthorhombic structure. C is the correct answer for this question. It's a very simple basic question. Now, which of the following is not a phase in steel? Which of the following is not a phase in steel? Remember, limonite is not a phase in the steel. Limonite is what, you know? Iron ore. Limonite is iron ore, that is in the iron ore. Iron is present in iron oxide form. So limonite is not a phase. Limonite is not a phase in the iron cementite phase diagram. So C is the correct answer. Right. So we discussed different questions related to iron cementite phase diagram. Good number of questions they asked. Crystal structure, very less number of questions, but from the material properties and testing, from the iron cementite phase diagram, they asked a very good number of questions. Now we will see the questions from the heat treatment process of steels. Okay. Heat treatment is nothing but to improve the mechanical properties of material. We are quenching them, we are heating the material up to certain high temperature. Then after that, we are cooling the material with the different cooling mediums. Like first, hardening process. In case of hardening process, we are quenching the material. So we are cooling the material rapidly so that martensite is formed, hard phase martensite. Second, if we talk about annealing process, we are cooling the material with a slow cooling process. We are cooling the material with a slow cooling rate, that is a furnace cooling. Okay. So by cooling the material with a slow cooling rate, so that we will get a coarse perlite. And by cooling the material in air, that we call it as a normalizing process, we will get a fine perlite. And tempering process is used to relieve the hardening strains and increase the toughness of material. And as tempering process is used to get 100% of bainite. Ma tempering process is applied to get 100% of martensite. And different surface hardness methods are there, like flame hardening, induction hardening, carburizing, nitriding and cyaniding. And one method that is used for non-ferrous alloys to increase the strength and hardness is precipitation hardening process. So these are the different types of heat treatment processes. So they will ask you some good number of questions from these processes. Now see here, why are gear teeth more harder? See, why gear teeth should be more hard? Because there should be a wear and tear. To reduce the wear and tear, to avoid wear and tear, the gear teeth must be having more hardness. The gear teeth must be having good hardness. Simple question. Gear teeth, again they asked a question, harder to avoid wear resistance, right? Dash surface hardening process gives maximum hardness to the surface. Remember, dash surface hardness will give you maximum hardness to the surface. There are pack hardening, nitriding, cyaniding, induction hardening. Here, pack carburizing, we can say pack carburizing. So this carburizing process will give you more case depth out of nitriding and cyaniding. So A is the correct answer. Pack carburizing process will give you more surface hardness. Now, heat treatment of steel is effective when the carbon percentage is lower than 0.8, cannot be used to relieve the local stresses and strains. We can use to relieve the local stresses. Can be used to change the carbon percentage. No, we can't change the carbon percentage. In case if we add externally, then okay, otherwise how is it? Involves heating steel to a temperature above melting point. No, we are not heating the material to above melting point temperature. This is also not correct. Okay, can be used. This is also not correct. So most appropriate answer for this question is A. So heat treatment of steel is good up to the percentage of carbon 0.8. Above that, because of more carbon percentage, the properties may not improve much. So A is the correct answer for this question. Right. Now, during quenching, martensite is produced. During quenching, martensite is produced. Yes, by quenching the material, we will get martensite. Right. Now, what type of cooling we are doing? Rapid cooling rate with a low cooling rate, with an appropriate cooling rate such that the carbon has time to migrate, medium cooling rate. Clarity. Remember, cooling time is equal to 1 by cooling rate. 1 by cooling rate. Now listen, the martensite is produced by quenching. Suppose this is a workpiece, I am heating the material up to 900 degrees Celsius, then after heating I am quenching in water. By quenching in water, the workpiece is going to reach to room temperature in a short period of time. Cooling time is low. If cooling time is low, cooling rate is high. Cooling rate is high. So high cooling rate, okay, high cooling rate we are preferring, so that low cooling rate is not correct, medium cooling rate is not correct. Okay, carbon atoms are not going to migrate, so rapid cooling rate, rapid cooling we are doing. So because of rapid cooling, we will get martensite in the hardening process. Now, dash process induces compressive residual stresses on a component to nullify the tensile residual stresses within the structure. That is short peening. That we call it as short peening. What is short peening? Suppose this is a workpiece. Suppose I am assuming there are some tensile residual stresses on the workpiece. So in a short peening process, what we are doing, we will consider a small spherical hard balls. We are applying forces, kinetic energies on the surface of the hard balls. So by applying kinetic energies on the hard balls, there are compressive residual stresses are generated on the surface of the component. Because of compressive residual stresses, these tensile residual stresses are going to be relieved. Fatigue strength will increase. That's why the short peening is the appropriate answer, most correct answer for this question. Okay, the process, short peening process induces compressive stresses on a component to nullify the tensile residual stresses, okay, within the steel structure. Right. Now, which of the following processes reduce the residual stresses within the steel structure? So we should reduce the residual stresses. We should remove the residual stresses from the steel structure. We should remove the residual stresses from the steel structure. Generally, we are doing heat treatment process, that is process annealing. Process annealing. Another name for this is stress relief annealing. Stress relief process annealing. Another name for this is stress relief annealing. So here we can say heat treatment is the most appropriate correct answer for this question. Heat treatment, by doing heat treatment, we can eliminate these residual stresses. We can eliminate these residual stresses. Next. So these are the questions related to heat treatment. Now the questions are related to steels and cast irons. I said from these steels and cast irons you should focus types of steels. Types of steels you should focus. They are like low carbon steel, second medium carbon steel, third high carbon steel. The percentage of carbons you should remember, for low carbon steel up to 0.3% of carbon, for medium carbon steel 0.3% of carbon to 0.36% of carbon, for high carbon steel 0.6% of carbon to some 1.5 or 1.4% of carbon. And also, okay, alloy steels, we are using stainless steels, all these things, okay, and high speed steels. And they will also ask you questions from types of cast irons. They will also ask questions from types of cast irons. You should focus on types of cast irons also. You should focus on types of cast irons. What they are? Grey cast iron, okay, grey cast iron, nodular cast iron or a ductile cast iron, nodular cast iron or a ductile cast iron you should focus, you should learn, and white cast iron, and grey cast iron, nodular cast iron, white cast iron, and malleable cast iron. Malleable cast iron. So you should focus on all these types of cast irons, types of steels and cast irons you should focus. Right. Now we will see the questions. Now see here. Cupola is the best suited for melting of. Remember, cupola furnace. Cupola is actually a furnace used to melt. Remember, cupola is a furnace that is used to melt cast iron. Okay, cast iron is produced from the cupola. Cast iron is a ferrous alloy. It is an iron carbon alloy. So the correct answer for this is C. C is the correct answer. Cupola is best suited for ferrous alloy. Cupola is best suited for cupola alloy. Hemant, we can expect questions from this subject, 5 to 8 questions you can expect. 5 to 8 questions, minimum 5, maximum 8 questions you can expect from this subject. These questions are very simple questions as I am discussing now. They are very, very easy questions they will ask you. Okay, no? Now, railway wheels are generally made of. Railway wheels and tracks are made up of perlite steels. Remember? Rail wheels are made up of perlite steel. This perlite steel having carbon percentage that is 0.8% of carbon. So approximately this is 0.8% of carbon we should prefer. So alloy steel containing 0.8 to 0.9% of carbon, we are using this perlite steel. Okay, no? Right. Now, next question. A steel whose elements are used for the purpose of modifying the mechanical properties of plain carbon steel is called alloy steel. Remember, if we add other alloying elements, some alloying elements we are adding to improve the mechanical properties of material, that we call it as alloy steel. Alloy steel is nothing but it is produced by the plain carbon steel by adding other alloying elements. Okay, by adding other alloying elements we are getting this alloy steel. There are so many elements like chromium, nickel, tungsten, vanadium, these type of elements we are adding. Now, carbon steel is, remember, option A, produced by adding carbon in steel. Option B, an alloy of iron and carbon with varying quantities of phosphorus and sulfur, purer than cast iron, none of this. Remember, carbon steel is nothing but adding carbon to the iron. Simple, don't go in depth, simple question. Percentage of carbon in steel. The percentage of carbon in steel is Remember, steel is an iron carbon alloy with the carbon percentage 0.008 percentage to, okay, 0.008 percentage to 2.1% as per the iron cementite phase diagram. But for applications point of view, we are considering only up to 1.5 or 1.4% of carbon, because above 1.5% of carbon, due to more carbon in iron, graphite formation is going to be happen. Graphite is going to be present in the steel material. That's why there is a chance to form a graphite. So if graphite is present in a steel material become brittle, that's why we are restricting the percentage of carbon up to 1.5. So here, this is the best appropriate answer. Up to 1.5 is the correct answer. Percentage of carbon in steel is up to 1.5. Now, hardness of steel depends on percentage of carbon. Okay, if carbon is more, cementite is more, martensite is more, right? It depends on amount of carbon present in it. Hardness of steel increases with increasing percentage of carbon. Hardness of high carbon steel is more than the medium carbon steel and low carbon steel. So that depends on the percentage of carbon. So B is the correct answer for this question. Next, in steel, main alloy causing corrosion resistance. Corrosion resistance, which material? Chromium. Chromium, if the percentage of chromium is more than 11%, that is stainless steel. Stainless steel is a good corrosion resistant material. So chromium is the basic element we are adding to increase the corrosion resistance. How the corrosion resistance will increase by adding chromium? Chromium in a steel react with oxygen and form chromium oxide layer on the surface. Chromium oxide layer on the surface is going to be formed. This chromium oxide is a passive layer. It is a passive layer. It will resist the reaction. That's why corrosion resistance will increase. So C is the correct answer for this question. Now, steel containing 18% chromium and 8% nickel, that is nothing but austenitic stainless steel. Austenitic stainless steel, 18-8 stainless steel. 18-8 stainless steels are austenitic stainless steel, because in that 18% represent percentage of chromium, 8% represent percentage of nickel. So austenitic stainless steel is the correct answer. C is the correct answer for this question. Next, first product of the blast furnace in the process of converting iron into a useful metal by reduction is a pig iron. Okay, from the blast furnace you will get pig iron. From the pig iron we are making different forms of iron carbon alloys like wrought iron, steel and cast iron. So pig iron has some approximately 95% of pure iron. It is in molten state. We can say it is a molten state of iron produced from the blast furnace. It is a molten state of iron produced from the blast furnace. From the pig iron, we are getting steel, wrought iron, cast iron based on the percentage of carbon. Right. Now, raw material for all iron and steel products. Raw material for all iron and steel products. What is the raw material? It's a very simple, that is nothing but a pig iron. If you want to make iron and steel, the basic raw material is a pig iron that is produced from the blast furnace. Now, chilled cast iron. Chilled cast irons are chilled cast irons are nothing but white cast irons. Hardness is very high. Machining is very, very difficult. High wear resistance. So out of these four options, softishness, no. Machined freely, no. High wear resistance. High resistance to wear. So C is the correct answer for this question. Melting point is lowest for cast iron. Cast iron has a low melting point temperature. So because of that, cast iron is the best preferable material used in casting process. Cast iron is a best preferable material used in casting process because it has low melting point and high flowability. Dash has high tendency to get work hardened. Brass is an alloy, it is going to be work hardened easily compared to pure metal. Brass is an alloy of copper and zinc. Remaining, these are our single elements, they are somewhat difficult to strain harden or work harden compared to the alloys, so brass is the correct answer. In 1841 high speed steel, the percentage of chromium, remember 1841 high speed steel, 18% represent tungsten, 4% represent chromium, 1% represent vanadium. So 4% is the correct answer. Chromium represent 4%. Tungsten represent 18%. Okay, no? Dash has least coefficient of expansion. Invar is an iron carbon alloy. It has a least coefficient of expansion. Okay, like tapes, measurement tapes are produced by the Invar material only. Dash is the essential gradient for any hardened steel. Dash is the essential gradient. Martensite is the gradient for hardened steel. Repeated question. Dash is used for bearing liners. Babbitt metal or a white metal is mainly used for bearing liners. Okay, Babbitt metal, lead tin alloy, it is also known as white metal. Babbitt metal is also known as white metal. It is used in bearings. It is used in bearings. Dash is the most important element which controls the physical properties of steel. Which controls the physical properties of steel: carbon, chromium, vanadium and tungsten. Remember, most important material, that is nothing but a carbon. In a steel material, the most important element is carbon only. By default, you can take A is the correct answer for this question. Now, typical stainless steels are alloy steels with, I said, what is stainless steel? At least minimum 11% of chromium is required. Then it is a stainless steel. Now see here in the options it is given 10.5. So see here, more than 10.5 chromium and more than 1.2% of carbon. Less than 10.5 chromium, more than 10.5 chromium and less than 1.2% of carbon. Less than 0.5. So here, more than 10.5% of chromium and less than 1.2, we are not, in stainless steel carbon percent is not very high. It is less than 1.2 only, right? So C is the most appropriate answer for this question. Mild steel belongs to which category? Mild steel and dead steels comes under low carbon steels. Remember, mild steel and dead steels. Mild steel and dead steel both comes under low carbon steel. Mild steel and dead steels both comes under low carbon steel. The principal alloying element of stainless steel is the chromium, because 10.5 or 11% of chromium we are adding. 11% of chromium we are adding to the stainless steel material. The main constituent of ferrous metal is iron. Ferrous iron. Very simple question. The maximum amount of carbon present in low carbon steel. I said the percentage of carbon in low carbon steel is up to the 0.3% of carbon only. Tool steel contain carbon. Remember, up to 1.5. 0.5 to 1.5, because tool steel has high amount of carbon, so that its hardness is more, its strength is more. Chromium in stainless steel increase the corrosion resistance. Simple questions here, repeated questions. Chromium increase the corrosion resistance. 1841 steel, 1841 high speed steel 18%, tungsten 4%, chromium 1% vanadium. 18% tungsten, 4% chromium and 1% vanadium. C is the correct answer. Which of the following metals contain chromium as its major alloying element? Chromium as its major alloying element, that is nothing but a stainless steel. D is the correct option. Which of the following is a non-ferrous alloy? Non-ferrous alloy. Which of the following is not a non-ferrous alloy? Read question. Not a non-ferrous alloy means which of the following is a ferrous alloy? Stainless steel. Remaining all are other than iron. Stainless steel is iron alloy, ferrous alloy. Dash is called a spheroidal graphite iron. Spheroidal graphite iron is a nodular cast iron or a ductile iron. In that nodular cast iron or ductile iron, nodules or spherical shape of graphite is present like this. Spherical shape of graphite is present. Now, some of the questions from the non-metallic materials, especially question they will ask from polymers. So, which of the following is a thermoset? Remember, from the polymers, they will ask you questions from thermoplastic materials and thermosetting materials. Which of the following is not a thermoset material? Nylon is a thermoplastic material. Nylon is a thermoplastic material, it's not a thermosetting material. Dash is not a ceramic material. Remember, bakelite is a polymer. Bakelite is a polymer, so it is not a ceramic material. Glass is a ceramic material, clay is a ceramic material, and aluminum oxide is a ceramic material, but bakelite is not a ceramic material. It is a polymer, that is a thermosetting polymer. Out of the following, which is an amorphous material? Glass is an amorphous material. Glass is a ceramic material. It is an amorphous material. Alloy of magnesium has light in weight. Light in weight. Less weight it has. So these are some of the important questions, repeated questions, expected questions I explained along with the revision of the important theoretical concepts. So by seeing these questions, what you understood? The questions are theoretical and the questions are simple basic questions, diploma based questions. If you have some basic knowledge on material science, you can easily attempt all types of questions. Questions are very easy, basic questions they are asking. Diploma based questions, right? So that's why even if you practice test series also, that is sometimes that is more than enough, right? So here we are providing, okay, test series SSC JE 2024 mock test, mega mock test we are providing on 26th May 2024, 1 p.m. to 3 p.m. in online mode. You just go through this test so that you'll get some confidence level. You will get to know time management, how to use the time effectively. Okay, your confidence level is going to boost up so that for your main exam you can do effectively. You will not do any mistakes in the main exam by practicing this type of test series. So all the best for your exam.